recording here. So last time we basically looked at what is this reference frame transformation and how can we transform from, typically in the stator reference frame, right? The stationary frame. People use it in different, in different terms, stator frame, stationary frame. It means, there is no speed, at least, everything is rotating with respect to you. So you are not moving at all, or you are not rotating at all. Now, arbitrary frame is any frequency including zero. So it's kind of the overall set that captures all the frequencies, including anything higher than zero. So you could be at synchronous speed. So arbitrary means, it kind of meaning is in the name itself. It could be any rotating frequency. Rotor frame or rotor reference frame implies it's with your frame is moving at the same frequency as the rotor or the motor rotor. So that helps us study the rotor variables depending on the type of motor, and sometimes the rotor frequency is related to the synchronous frequency, which makes the machine become simpler for analysis. So we've been talking about that. We've been looking at the independent elements R and L, what they would become if we do a reference frame transformation. And today we are going to look at a very simple example, just an RL three-phase circuit, three-phase RL circuit. Same R value, same resistance value, same inductance value, and then there is a mutual inductance that couples, like it would do in a motor. The only difference we have here with respect to a synchronous machine, permanent magnet synchronous machine at least, we don't see the back EMF here. Back EMF term is not here, so this is a good next step for us to study this, at least apply what we have looked at. And then, so typically we define the phase voltage, so VAS, that is from neutral to this point, that's VAS, VBS, and then VCS respectively. Okay, and then we like phase voltages, but keep in mind for a three-phase system, in a three-phase system, phase voltage is not the same as line-to-line voltage if it's a Y-connected network. Okay, and I'm sure you remember this from your power class. Now we can write our VAS total voltage here as the voltage drop across the resistor, this voltage, plus the voltage drop across the inductor, right? So we break it down into the two voltages, so we can apply the same concept to VBS and VCS. Now, when we do that, we can bring the topics or the concepts that we discussed earlier, because we now know how to transform any resistive circuit to the rotor reference frame. We know how to transform the inductive circuit to the rotor reference frame or arbitrary reference frame. I keep saying rotor reference frame, and that's a hazard of the field I'm in and the machines I'm working with. I'll try to catch that, but mostly I work with synchronous permanent magnet synchronous machines, so I tend to use that term automatically. Okay, so we can break them into these two voltages for each element. Now, with that, if we look at our rotor reference frame, again I said that, arbitrary reference frame variables, because rotor reference frame is not necessarily the arbitrary reference frame, right? So we are looking at this arbitrary reference frame variables. So we QS the quadrature axis, direct axis, and the zero sequence voltages. Once you transform those voltages, right? If you are to take these voltages independently and transform them, you're going to get these six voltages, right? They are now in that reference frame. We have transformed it. And based on what we discussed last time, the ABC frame voltages for resistance have no influence, because remember, we had our resistance matrix be a diagonal matrix, right? And we showed that it has no influence whatsoever when the transformation is applied to a diagonal matrix. It just stays like that. However, we showed that if we have a coupled inductance, not inductance just on the diagonal, but if you have an inductance in the following form, LS, LS, and then M, 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 M. So this is a balanced, a symmetric winding set, ideal at least, ideal symmetric balanced winding set. When you do the transformation, we said it will have this form of voltages. It will convert into these, and then these flux linkages can be written using these current and inductance terms, assuming a linear machine. Okay, so only valid for linear operation. If your machine is under saturation, this all breaks down. Okay, so keep that in mind. We have covered this already. So now we can actually take these and directly substitute into our equations here, which gives us a very nice relationship like this. Okay, so we have our VQ quadrature axis voltages in this form, direct axis voltages in this form, and the zero sequence voltages in this form. Okay, and the importance here is, previously we had a coupled circuit. To remember, if we go back to our circuit, there was magnetic coupling. See, we had this circle, which means all these inductors are coupled to each other through the material that we have in the machine. But now if we draw the new circuit diagrams, they are all there's somewhat coupling, but we can draw these kind of simple circuits based on just the voltages. There is no magnetic coupling. Okay, so this is the relationship, or at least this is what happens when you transform this three-phase RL circuit into this reference frame using the transformation. Okay, and depending on what type of a reference frame you're using, we can drive some of these voltages to zero. So that's an advantage that we are going to have when we analyze a machine. Okay, so this is just an example. Feel free to start with these original equations. You can derive them on a piece of paper yourself, apply the transformation. I encourage you to do that. That way you will see it for yourself that these are the true equations that you're going to get, and you can even apply it to any frame of reference. All right. Okay. So this is one application that we can use our transformation, or the reference frame transformation. We can transform variables, machine variables. If you are working with power systems, you can transform those power grid models. You have a three-phase inductance, three-phase resistance, three-phase capacitance. You can transform all those using this reference frame. So that's for variables, right? Machine variables, so power system variables. We can also apply those same concepts or same transformation for measured signals like voltage, current, and if you can calculate or measure flux, you can apply the same concepts to such measured variables. Okay, so what I want to do is, I want to first of all just go over what these variables will look like. Okay, a couple of things here that I want to capture. Now, are coming up with this three-phase set. For now, we will assume a balanced set for our initial understanding. Okay, and then we have a magnitude of capital Fs. This can be represented as a square root 2 times Fs. And then what does this mean then? If this is our peak, right? This is our peak. When we say in this term root 2 Fs, what does that tell us? You should remember this from, the topics that we have been discussing. This is our RMS value. Okay, so there are two forms of representing the same idea. So if we represent F as this is going to be RMS, because it's root 2, that's your peak value. But if someone represents your signal with just an Fs times cosine, this Fs implies that is your peak value there itself. Okay, and I'm using F as a generic variable. This F could be a voltage, so you can substitute F in every place in this expression. It could be current, it could be flux density. So I'm just using a generic variable so that we can capture or apply across the board for many types of variables. And here I'm showing the theta angle because we have a three-phase balance set and we have an angle, right? Because it's a sinusoid or a cosine, it has an angle. And then I'm saying this is the electrical angle, theta E. F means corresponding variable. If we chose to go with voltage, then this is going to be theta EV, which is the voltage angle, the vector position of that voltage, right? So that's basically, this is voltage. It's going to be that vector position at a given instance, right? So how can we know the position? What do we need to know position? For a signal, if we know frequency, omega E, right? Omega EV, at least for voltage, if we know our angular velocity, we can actually compute theta. How do we compute position if you know angular velocity? What do we need to do? Integrate, exactly. Very good. Yeah, you need to integrate, right? So the integration, if it's known at every instance, you can find theta. But when we go into applications, we will have our own position measurement scheme that gives us theta as a measurement so that we can perform our transformation. Okay, so these are the signals coming in. Let's assume they are balanced, and we need to understand what balance means. Balance means, see, all of them have the same amplitude, and all of them are 120 degrees out of phase, right? So plus 2 pi by 3 is equal to negative 4 pi by 3. I hope you guys understand that. Okay, they mean the same thing, and they are cosines and they have same amplitude and they are out of phase by 120 degrees. So that is what we call a balanced set. Okay, you deviate from that, then your results are going to deviate from what you expect it to be. All right, so now we have these signals. They are, let's say we have a generator, don't want to name them. We can have a three-phase power source that is generating these voltages or currents, and now we need to transform them, right? Let's say we know the frequency. If we know the frequency, we can basically apply our transformation directly. This Ks discussed earlier. Okay, let me pull up that sheet just to show you what that transformation is. So it's this transformation, and then for now let's assume we are transforming it to an arbitrary reference frame, not necessarily the same frame as our signal. Okay, so what that means is your signal might be rotating at, let's say, 100 hertz. Okay, it might be rotating at 100 hertz, and you are trying to look at that 100 hertz signal from a frame or the reference frame rotating at 50 hertz or 20 hertz or 1.1 hertz. So so it's an arbitrary reference frame, right? So if we do that, then the theta that we use in our transformation is based on that reference frame's speed, the speed of that reference frame, omega, which may be different from the actual signal frequency, maybe not. Okay, that's why we call it an arbitrary reference frame. Why we call it, it's just for the learning purposes, just to establish a general understanding. Practically speaking, we'll have only few of these reference frames that we use. Okay, but we know we need to build up the mindset that this can be any reference frame and not just the rotor or the synchronous frequency, because sometimes this might help debugging certain issues. Okay, Garrett, did you have a question?
No, my Wi-Fi was messing up and was like disconnecting me and stuff. Sorry.
Okay. So for now we'll assume our reference frame is rotating at omega, and our signal frequency is at omega EF for now. Okay, and once we do the transformation, we're going to get this relationship. This is F. So and you can again use the matrix. You can do the multiplication yourself. You can use even MATLAB symbolic toolbox. You're going to get your FQS be Fs cosine theta EF minus theta. These two theta positions are different because for now we are only considering a signal of two frequencies, two different frequencies. This is the signal frequency. This is the frequency of the frame that we are looking at it from. Okay, and then for QS, it has a cosine nature. DS, it has a sine nature. We have a negative sign here, and then we also have our zero sequence, which is 0. Okay, so this is under this balanced condition, and we are rotating at this omega frequency. Okay, so now what I want to do is instead of looking at these signals from the omega, this arbitrary reference frame, let's get to the same speed as the signal. Why not rotate as the same frequency as the signal? And now we can see what is going to happen. Okay, so when we do that, omega EF becomes omega, theta EF becomes theta, assuming there is no offset between the two signals. Okay, and when we do that, very beautiful thing happens. See, now our Q axis, since it's aligned with the signal, that sees the full amplitude. D axis, direct axis, which is 90 degrees orthogonal, that's 0. Right, the projection of it is going to be 0, and then of course 0 sequence is going to be 0 itself. Okay, so do you guys get this? Do you guys understand what's going on here? What we did, at least in terms of transformation, we set the same frequency, and then mathematically we get a very nice result. Okay, so I think this simulation is going to make it a little bit more clear. So I'm gonna show you a very nice simulation here that shows what this reference frame transformation does. So give me about a minute here to get this set up. Okay. Oops. Then
I guess I do have a quick question.
Yes, Michael, go ahead.
What is the, so I see FQS equals 0.1, or is that, what is that?
You mean this one?
Yeah, it looks like
This
it's
is
0.1
times 1
times.
because,
Okay.
yeah,
Yeah.
because when theta EF equals to theta, cosine 0 is 1,
Okay.
right? So this
Yep.
term becomes 1 and this term becomes 0, therefore this term is 0.
Yep.
Okay.
Okay.
All right. So let me share my screen with you guys. I'm gonna turn off the document camera, then screen 2. Yeah. Can you see this? Is this clear?
Yeah, it's in the left side of the screen, but yeah, it's there.
Yeah.
I can see it.
Yeah. So good. Okay. Still recording now. I want to show you a couple of different ways we can establish or generate a position signal, and both ways are valid. First one is using a ramp. Okay, so ramp basically sets the zero speed. It kind of sets the slope for the signal, and then it's going to generate a ramp. And the alternate method is basically set a speed and then integrate that with an integrator, and you can obtain position. Okay, and you'll see that the result is the same for both waveforms. Okay, can you guys see this? Not sure if it's clear enough. Is that clear enough? Okay. Yeah. So see, you can see that they give you the same result, same slope. So you have a couple of different ways of obtaining this, coming up with this frequency, or the position signal, if you are to develop a simulation for a motor or to demonstrate this. Okay. So I wanted to show that first because different people uses different methods to generate their signal, for the position signal at least. Okay, and then the second is, now I have 3 sine waves. Okay, 3 sine waves, and let me go inside them. Here I have set the amplitude to be 5. Okay, frequency to be at 50 hertz, 2 pi f, that's 2 pi f radians per second, and then I want that to be a cosine. Okay, so I'm including a pi by 2 phase shift here. Okay, and then this is to demonstrate something later, so don't pay attention to that. So it's just adding a pi by 2 phase shift here. And then say, okay, so I go to the next waveform. That is again 5, same frequency, and then pi by 2 minus 2 pi by 3. This is 120 degrees out of phase. This is the FBS. So we can even name them, right? You can call this FAS. You can call this FBS, and you can call this FCS. Okay, so and then if you go inside here, you're going to see the same relationship. We have the pi by 2 phase offset to make it a cosine, and then we have negative 4 pi by 3, which makes it again 120 degrees out of phase. Okay, so we have these three phase signals, could be voltages, could be currents, and then I have this position signal, which is aligned with my same frequency as my signal. So first of all, I want to try the arbitrary reference frame. Okay, so let's go to a somewhat of a different frame for this, for the initial run, because we are treating it as an arbitrary frame. Right? So let's say we are running at 20 hertz in the arbitrary reference frame. So you have your arbitrary reference frame rotating at a lower frequency than the signal frequency. Okay, so that's how I have it set up. And then here, this is this function, the MATLAB function I spoke about last time. And let me open it up and show you what I have inside it. Okay, so can you guys see this? Not sure if it's very clear. Okay, so it's basically, you know, a function that I have set up which does the transformation for me. Okay, I have my A, B, C, and the theta, the inputs coming in, and I'm doing the transformation using our reference frame transformation computation. So this is what you need to implement to do reference frame transformation, whether you do it in a real-time system or whether you do it, you know, for your simulation. Okay, now in practice, when they need to implement cosine, sine in an embedded platform, typically people tend to use either approximations or a lookup table. Okay, both works depending on how much resources you have, how much accuracy you want. So then, you know, out comes my computed outputs, the reference frame transformed variables. Okay, so let's just run this. All right, we can look at the three-phase voltages. So I'm going to place my first plot here. Okay, and then my output right here. So we'll leave them like that so that they'll show the result. Okay, and let me even run this for even a shorter cycle to see if we can get a very nice view of the waveforms. Okay, there we go. See, now that's very nice. We have the cosine waveforms, all right, and then since we are rotating at an arbitrary reference frame at 20 hertz, now we can see that those signals that are in the reference frame also look sinusoidal. Okay, and then what we can do is let's actually go further away. So we have our reference frame, our signal frequency at 50 hertz. Let's go down to maybe 5 hertz. So we are going away from the signal frequency, right? Let's see what happens. Ooh. See, it's somewhat it's still sinusoidal. You're still going to see a significant difference here, right? Let's try maybe how about 30 hertz? 30 hertz. So it's still an arbitrary reference frame. Yeah, see, now it's kind of stretching out and we can't even see what the difference is. So maybe have a little bit more frequency here. Yeah, see that because of that rotating frame being a little bit more closer to our actual signal frequency, the difference is less, right? So you can see a little bit more elongated, or the relative difference becomes lower. Okay, so now let's try actually to go to the stationary frame. Stationary frame is what? What is the frequency of the stationary frame? Can you guys tell me? So when we say stationary frame, what's the velocity on the stationary frame? Well, technically speaking, stationary frame means what's the frequency? Technically speaking. 0, exactly. Yeah, very good. 0 hertz, right? So when we set 0 hertz, with respect to stationary frame, we're going to see the same frequency. See, same frequency as the signal, right? So that makes sense. So we are at, so our, if you look at the notes, right now our omega is 0 and omega EF is at 50, right? So that makes sense from our equations. Even after the QD transformation, you see the same frequency as your original signal. Now, let's go to the same frequency as the signal. Okay, we can call synchronous frame. Synchronous frame. We are now going to be in synchrony with the actual signal. I don't know, is synchrony a real term? I don't know, I'm not sure. So let's make our reference frame operate at 50 hertz too. Okay. Now, when we have the reference frame operating at 50 hertz, what do you guys expect to see? What do you think will happen? Any predictions? Okay, so Alex is saying we want to see constants once transformed. Okay, let's see if we get that. Oh man, look at that. Look at that. So that theory is true, right? The theory is true. Since we are going at the synchronous frame, we have constant signals. We have the amplitude fs here, 5, right? And then d and 0 both are 0. So that's why we see this overlapping waveform there. Okay, so that makes sense. So now if we can come up with a strategy to know position every time for the signal, we can make them look like DC using this transformation. Very cool, right? So this is what this field-oriented control rotor reference frame transformation does to your signals, and it makes your AC signals look like DC. Okay, is that understand? So we are looking at that signal from a different reference frame. Now we can implement controllers for this signal, and then we can transform them back using the inverse transform, bringing it to the right frame or the stationary frame, where now we can apply the voltages to the motor, which makes our life so much easy. Okay, so all right, so now we know how to work with these signals. We can transform and transform them back, but what will happen if there is an imbalance? Alex, you have a question? Well, so now be careful, Alex. When you are saying when we influence the DC-like signals, all those DC-like signals are hypothetical. They are only in your computer. They are not in your system, right? So what you're basically doing is you're taking your actual AC signals and you are converting them to a new reference frame. So that means you're only looking at them from a different perspective so that it looks like DC, but you're not influencing your original signals. Okay, yeah, so you're not affecting your signals, you're not influencing them, but now you take those signals, you convert them to DC, you develop your controller will run in this hypothetical domain, and then it'll say, you know, hey, you have 5 volts, I want to regulate it to a certain value, so apply this much of voltage, and that amount of voltage it is asking you to apply will get converted back to this frame using the inverse transform, which will make that DC-like signal from here to an AC that gets applied to the machine. So we'll talk about that in more detail when we come to that algorithm. Okay. For now, we're trying to understand, okay, we can do the transform, we can go into this reference frame, and it makes the signals look DC. Okay. So it looks perfect, it looks very nice and dandy, but what will happen if the balance condition is not valid? That means we have imbalanced signals. Okay, we are still in our right reference frame. Let's implement or let's introduce an imbalance condition. Okay, so I'm going to make VAS a little larger in amplitude than the other two signals. So I'm going to inject like 0.2 additional. Okay, and then let's see what happens. Ooh, look at that. Right, I don't know if you can see here Let's inject a little bit more. I want to make it look significant. I don't know if you guys can see that. Let's make this, make it 6. So makes it 6 and then, okay, see, now you can see that, right? As soon as we made it in balance, our phase A is much larger than B and C. And now, even though we are in the rotor reference frame, we are seeing some sinusoidal signals. Okay, so this is very practical issue you're going to see when you work with machines. If you see in the rotor reference frame, if you see some harmonics, that means you are not applying a balanced set, or you don't have balanced currents in the machine. Okay, so that's one way we can have an imbalanced set. The other way we can achieve an imbalanced set is change the phase. So actually, let's just modify. So here I'm introducing a little bit of phase here. I'm going to make this a pi by 60, very small angle change. Let's see what happens. See, there's a slight phase shift here, but you can see that the currents are they're not DC-like, right? They have some harmonic in here, and worse the phase shift gets, worse the imbalance reflected on the rotor reference frame, or that frequency, this synchronous reference frame, right? So that has a direct influence on the transformed variable. So we have to be very careful. Let me make this 0, and we can go back to our original properly transformed variables. So now there's no offset, no error. It's back to DC. Okay. So we looked at the imbalance, and so that showed at what it does. And then let's look at another effect that we can see, an offset in the position. What this means is, so you have one frame rotating at, let's say, so let me try to say that both frames are rotating at the same frequency. The signal reference frame or signal frequency is the same as your reference frame frequency or the reference frame speed. However, they have a relative offset, which means they are slightly off in terms of alignment. They are moving together with each other, however, with a slight offset. Okay, what do you guys think will happen if we have such an offset? Any thoughts what that's gonna do to the system or the transformation here? No idea? If you have a relative misalignment between the actual speed and the reference frame speed. So the speeds are the same, but they have starting at two different speeds. Amplitude shift. You mean in the AC signals or the DC signals? Okay, for the DC. Okay, let's see. So let's introduce a initial angle, right? So let's say we have pi by, well, it's 0.2. It's 2.2, 0.2 radians, right? So it's off by 0.2 radians. Exactly, right? So our original signals are not affected because they are there. They're not going to get influenced. But since we are looking at a slightly off reference frame, the amplitudes that we see in the reference frame are slightly affected. See? Now we have some amplitude for D, and the amplitude for Q is reduced. right? Zero sequence remains the same. Okay, the zero sequence remains the same. We can even introduce a little bit more. What will happen if we go to 0.5, right? 0.5. See, it's the Q is getting lowered and the D is getting higher and higher. Okay, and we can even introduce a pi by 2, let's say pi by 2 phase shift in our reference frame. See, now D is aligned with where Q should be, and Q is actually under this red line, red waveform. Okay, so this is a practical problem. If you don't get your position sensors aligned, this is what what's gonna happen to your signals. You think you are measuring one thing, but you're actually measuring something else. So you have to be very careful when this position offset is connected to your signal, to your system. Okay. We looked at that. We looked at imbalance, amplitude change, and we looked at the phase shifting, right? The whole set. Did we shift? Yeah. Offset to position, and then phase shifting the whole set. Did we do that? Phase shifting the whole set. Yeah. Yeah. Okay. So let's make sure it's properly aligned. Yeah. So now this is without that offset. Okay. So does that give a good idea of what this reference frame transformation does to signals? Yeah. Okay. Good. Any questions? Anything you would like to see in this simulation? Now again, you can have harmonics go in here. Instead of 2 pi 50, you can have a couple of more signals go in here, and then what that does to your signal. So there are different things that you can try with this signal, but yeah. So overall, this is the effect, and this is what happens with reference frame transformation. Okay. Good. Okay. Good. Good. All right. So let me stop the recording here.